We solid? Good. Yeah, we're going to need, you need basically one per hypothesis test, and I'm predicting we're going to do 3 of them today. That's my prediction. I'm guessing. We might get 4. We'll see how time goes. But I'm thinking 3. I'm thinking 3. So, and we're going to take our time through this first one, because I want to make sure you guys understand the underlying structure. You understand the conclusions now. I totally get that. But I want to make sure you understand the underlying structure, the mathematical structure of what's going on. Once you understand the mathematical structure, we let technology do the math for us, and we focus again on the interpretation and the results. But I want to make sure it's not just black magic math that's happening. It actually is something that's tangible. So we were testing a flu vaccine. We were testing a flu vaccine. Okay. We were kind of halfway in the middle of this one last time. We know the flu rate in the general population is what? 12%. From historical statistical evidence, 12%. 12 out of 100 people get sick. Roughly every 8 people, one gets sick, roughly. Okay, so we know the historical flu rate, 12%. So we're a pharmaceutical company. We want to fight that and make our stockholders happy by making a lot of money for them. So we develop a flu vaccine. We want to see if it works. We'll test its efficacy. We give the flu vaccine to 1,000 people. Of those 1,000, how many get sick? It was 1,000. Yeah. 101 get sick. 101. So now the question is, does the flu vaccine appear to be working? Now, we can't answer with any kind of definitive yes or no, because we never know yes or no. We know it's most likely working or it's most likely not working. It's like any other jury trial, if you think about it that way. It's like any other jury trial. It's most likely, it looks like it's working or it looks like it's not working. So what do you guys think? If you divide those, p hat, you get 101 out of 1,000. Keep writing 100. Which is 10.1%, right? That's less than 12. So it's working. Oh, good. Good. That was very quick, by the way. Oh. Good, good. Very, very quick. I've been timing you guys. My 243 still have to wait a couple seconds. So like, wait a minute. You're forgetting something. What am I forgetting? Always. Always, 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 because you didn't infect every single person in the population with your vaccine and see what happened to them. That's the only way you could say without a doubt if it came in lower than 12%. We only have 1,000. So that means we have uncertainty. We have sampling error we have to deal with. Now, one way to do it is to build a confidence interval. Aaron, I think this was your idea at the very end of class on Thursday, if I remember correctly. Why don't you just build a confidence interval? That's a fantastic idea. I wish we would. But you have to develop what's called a one-sided confidence interval. Sean, you asked about this after class. I appreciate that too. Your TI doesn't do it. Most technology doesn't do it. As a matter of fact, I've only found it in one site online, and it's a .gov site. So nobody uses them. I wish that was not a true statement, because once you understand two-sided intervals, shifting the areas around to make them one-sided is actually just a quick little mathematical thing, but nobody does it. What they do instead is hypothesis testing. That's what you're learning today, which we're going to be doing the entire rest of the term, is essentially one-sided confidence intervals. It's how to set up a one-sided without actually setting it up. Bear with me, and I'll show you what I'm talking about as we go through today, and Thursday, and week 7, and 8, and 9, and 10. You'll see where the intervals show up on the curves as we build them. It's just nobody calls them that anymore. Is that fair? Maybe. Maybe it's fair. Maybe not. We'll get there. So, before we start, what's on your mind, Ann? Ask me that question. Just taking it in right now. It'll create. Good for you. Good for you. Now, if you remember, we set up the first part of this together. We are testing the parameter little p. As flu researchers, what are we interested in? Or as not flu researchers, but as flu vaccine creators, what are we interested in?
Which one are you asking?
No, I was actually asking what p is, little p is. We're testing a variable, right? Little p, we decided that was the variable. We're going to test percentages versus averages. Percentage of what? People got the flu after they get the vaccine. That's what we care about, right? That's what we don't know. We know that in the general population, 12% of people get the flu. What we don't know is what appears to happen once we inject them with our vaccine, right? So that's what, I'm just kind of doing a quick recap of how far down we've gone so far. Very, very good. So we are interested in the percentage or the flu rate of those that are vaccinated. So I know what it is, right? It's 10.1%. You guys already poked a hole in that logic. Good for you. Suppose the flu vaccine maker said, I heard it's 9%. Yep. Trial test, 9%. And the public goes, no, it's not 9% either. So what do the flu vaccine people try to compare it to? Instead of trying to make up some fabricated percentage that makes their product look great, or worse, it's 50%. It's a coin flip, get the flu or not. What number do they start with?
People who get the flu.
Right, in where? In the general population, and they compare their result to that result and try to show that they are... Exactly. I was going to say different, but lower is a much better. I was saying different, which is actually a confidence interval. You're saying lower, which is a one-sided confidence interval. Very nice, Aaron. Yes, that's what I wanted to hear. So that was the hypotheses, Elizabeth, you were giving me now. This is step one. Step two was setting up those hypotheses, right? The null and the research. I personally like to start with the research hypotheses every time, because that's what the flu vaccine makers are trying to support. What do they want to see happen with people that get the flu vaccine? What do they want to see?
Less than 12.
They want to see less than 12. That gobbles up all those silly 10.1%, 9%, 8%, 7%, 6%. When you see less than, now of course the question that you guys are going to ask, and I think you did ask, was, who said it? Nice and loud. Tyler, thank you. How much less than? And the quick and easy answer is, don't say with a number.
We don't know.
If you want to support that hypothesis, it's not so much a numerical value of how much less. You're just going to show that it is significantly less. And the word significantly, when you apply it to inequality, varies with that sample size. When that is huge, it doesn't take much of a change to indicate significance. More on that soon. More on that as we play with this example, because that's where technology really helps us out. So significantly less. Okay? We can measure the significance later, as we did on your last exam, which you guys totally crushed. But here, let's just worry about, we're going to show significant decrease in those that got infected. The null hypothesis, therefore, is everything else. Greater than or equal to. If it stays at 12%, that means you're basically injecting nothing into their blood. If it's greater than 12%, that means maybe you should stop making whatever you're making and stop putting it in people's bodies. Cool? Good so far? Maybe-ish, getting there. Then we did an error analysis, and I think you guys did a pretty good job of that, right? False positives, false negatives, making sure which one is which. Which one's a false positive? Remind me again.
Said it worked when it didn't.
No, it said it worked when it didn't, and that's called, what is that called? Of course we have to call it something different because we're annoying. That's a type 1. You say the vaccine is actually doing something in the general population when it isn't. So false positive here, take my placebo. False negative, type 2, would be
Saying it doesn't work when it does.
good. The vaccine does work, but you missed it on your test. And then I had you guys decide which one you would rather avoid. It sounds like most of you guys wanted to avoid a type 2. I'm kind of with you on that one. Knowing you have a cure and then not seeing it. I'm tempted to agree. All right, which distribution are we going to look at? This is where we stopped. We're down at step 6 now, it looks like.
Z.
Where's Z? How come?
Our sample's greater than the...
Yes, ma'am, yes, sir. We're looking at a proportion. This is a lowercase p, FYI, by the way. We're about to get a big P, the P value. But this is a lowercase, it's a proportion. The sample proportion, p hat, is part of the calculation of what we're about to do. But yeah, just realize you have to use a Z distribution for this one because of the fact we're dealing with proportions. Good so far? Ask me any questions up to that point, because now comes the fun part. Now we actually start doing the numbers. It's fun for me. It might be annoying for you guys, but you'll see the working in the ins and outs. Cool? Cool thus far? Any questions? We're decent. Okay. No, we're content anyway. All right. Now, this is about as far as we got last time.